Now let's look at a severe weather scenario characterized by a rapidly changing mesoscale environment. First thing to note is I swapped the 500 to 300 millibar ALPW layer for the GOES 7.3 micron water vapor imagery for reasons I'll describe in just a minute. Low-level moisture advection, depicted in this upper left panel, readily shows moisture from the Gulf of Mexico moving northward towards this cyclone further to the north. However, there's some caveats in here. You see some abrupt changes during that loop, and to focus in on that, I'm going to stop this at a particular time. Stop this at 6Z, and note the low-level moisture distribution looks like this at 6Z. However, at 7Z, it looks very different over this area. I'll go back and forth, and you can see why. What happened is a new satellite pass came in for 7Z, so we have newer information available for 7Z, and then remember the GFS will just take that and advect it until the next pass becomes available, and then we see another abrupt change a little bit later. So I'll go ahead and stop that a little bit later. Another change takes place from 18Z right here to 19Z, and go back and forth again, and you can see, similar to the earlier pass, you can see some abrupt changes that have taken place in the moisture, and again, just due to the satellite pass, the more recent satellite data that has come in. This looks different compared to a model output, for example, of some moisture field, so it does take some getting used to, but that's how you interpret the imagery that is available from the ALPW product. Mid-level dry air is also observed in the 700 to 500 millibar layer down here, and can be useful in detecting dry air associated with the EML, the elevated mix layer. If we combine that with the 7.3 micron band shown over here in the lower right panel, we look for these regions of warmer brightness temperatures that develop during the daytime off the elevated plateau regions of Mexico and the southwest US. Advected downstream are these regions of warm, drier air, and these are characterized by an EML. Now, you need to verify an EML is in place by looking at soundings. We'll go ahead and look at a sounding from Fort Worth, Texas at 15Z. And here's that sounding. ALPW is well suited for this type of application where we have different moisture distribution across the vertical. At low levels, you can see moisture from the Gulf of Mexico. Above a capping inversion, you can see drier air off the elevated plateau regions of the southwest US into Mexico. This region is characterized by the elevated mix layer, where we typically have very steep mid-level lapse rates, and that enables higher CAPE to be achieved. Now we go back to our animation, and keep in mind that these regions of mid-level dry air that may be associated with the EML may have these abrupt changes as well. For example, here's the 20Z image, and if we compare that to 21Z over here in Texas, you can see a pretty big change. And again, that's just associated with the new satellite pass that comes in. Generally speaking, the EML can be detected if it's dry above 500 millibars. If you start to see indications of more moisture at upper levels, that may obscure an EML from being detected here. So that's just something to keep in mind when looking for the EML.